In this video, I want to focus on rational inequalities, and it's going to be a very, very similar process. So it's when you have a rational function that is less than, greater than, less than, equal to, or greater than or equal to 0. And again, your first step is going to always be to bring everything to one side so that one side is 0. Here's where it's a little bit different with rationals. If you're not already 0 on one side, when you subtract or add to the other side, it is typically a little bit more work because we often have to find common denominators to actually add or subtract when we bring things over. So it does get a little bit more complicated. If that right side is 0, then it's not as bad. You already can start right off the bat, but I'll show you an example there. And then to find the boundary points, you actually solve both the numerator and denominator equal to 0. So that is a change. So it's not just the denominator or just the numerator, you do both of them equal to 0. And those real values become your boundary points. And then from there, the process is going to be very, very similar at the end. One thing I will note, and we'll see this in example, is you do want to watch out your denominator being undefined at the end. And I'll show you this when we get there, okay? So being undefined at the end. So let's do our example first. So here we have a rational, and then we have a 2 on the other side. Again, if the other side was 0, it's actually pretty straightforward. You would just start with setting both numerator and denominator equal to 0. But if it's not, you do have to bring that 2 over. So you have x plus 1 over x plus 3. Minus 2 is greater than or equal to 0. So what happens here is you do need to actually combine these because I need to have it as one numerator and one denominator all together. So the 2 is over 1. And if one of your values is over 1, then it's pretty straightforward to find a common denominator. You would just use the other denominator and multiply it on both the numerator and denominator here. So our goal here is to still find a common denominator. Even if you have x's, you're going to have to find a way to make that work. So here, 1 doesn't really do anything. So the main denominator is x plus 3. So I'm going to use that factor and multiply it over here. Now I will have x plus 1 over x plus 3 minus 2 x plus 3. And then here, I don't really need the 1. So you can see I do have those common denominators, and I can actually go ahead and combine it together. So I have x plus 1 from the first group minus 2x plus 3 from the second group, all over x plus 3. You do want to distribute here. Be careful you're distributing the minus sign as well. So I have x plus 1 minus 2x minus 6, all over x plus 3. And then finally, combining my x's together and my numbers together, we put everything as one rational. So that's where it gets a little trickier because you do have to do sometimes some work with common denominators first, which is a little bit harder here. Now, if you need some help with working with rationals like this, section P6 in your text actually goes through rationals and reviews how to do things like adding or subtracting, multiplying, dividing, things like that. So you can check that out there as well if you need that little bit extra help. All right, so now we have our starting piece here. So this is what you want. Everything is nice and organized. I have just one rational and I have 0 on the other side. So what you do is you set both the numerator and denominator equal to 0 to solve. So here I'm going to add 5 first, and then I would divide by -1. So I have my first boundary point of -5. Here I subtract 3 and I have my second boundary point of -3. So again, it's where it's a little bit different here in the beginning. So you have your numerator and your denominator set equal to 0. And that's how we get our boundary points. Okay, so one boundary point and another. Now the process is going to be very similar here. I do need to pick some test points. So I'm going to choose -6. I'm going to choose -4 in here. And then here I'm going to definitely choose 0. So you can tell I tend to choose 0 because it's usually pretty easy to plug in. And again, we really just need to know if it's positive or negative. Now I'm going to use this one right here. So you want to just use that simplified version. And it's really important that you haven't made any mistakes, right? So if you're not sure, go back, check your work, because where we're not starting with the original problem, there's chances that this could be wrong, right? So you want to go back and really take your time and make sure you haven't made any mistakes there before you keep going. Now I'm going to plug in -6. So I have minus -6 minus 5 over -6 plus 3. Here my two negatives will cancel. So I'll have 6 minus 5 is 1 over -3. And again, all I really care is if it's positive or negative. Now I plug in -4. So I have a negative and then -4. Oops, -4 plus 3. So here I would have a +4 minus 5 is -1 over -1, which is +1. And then for the last one, when I plug in 0, I have 0 minus 5 over 0 plus 3, which is -5/3. Again, I don't really care about the exact value. I just need to know if it's positive or negative. So here we're looking for greater than or equal to 0. So we're including the 0 values here, so those endpoints. And I want positive, right? So if it's greater than, I want positive or 0. So I'm looking at this region right here. So I'm looking at -5 to -3. Now, here's where that little part that I mentioned is going to come in, where I said you need to watch out for your denominator. And this is really going to only be an issue if you're having equal 0. If you don't have the equality piece, then you're using parentheses anyway, so it's not going to matter. But if you're including the 0, you have to be careful that you don't include the one that makes the denominator 0 and undefined. So notice that here, if I plug in -3, that would make my denominator equal to 0, right? So this is undefined. So even though we want to include the zeros, I cannot include -3 because it would make that denominator 0. That is a problem. So even though it's a valid boundary point, it cannot be part of my final answer. So I'm going to change this to a parenthesis here as my final result. Okay, so that's my warning with rationals. We don't have that issue with polynomials because we don't have that denominator. But with rationals, if you are including the boundary points, you need to be careful that you're not including the one that makes, or ones, whatever, that make the denominator 0. So be really careful there in your final answer. And this is a really easy thing to miss if you're kind of going through quickly and not noticing that. And then if you want to graph it, so what your graph would look like here, if you have -5 to -3, is this side would be a bracket, and then this side would be the parenthesis. All right, let's check out Desmos here. So I'm going to show you this one right here, what we just did. And then I'm actually going to show you what the original looks like too, so you can kind of see how the graphs look both cases. But again, I think the 0 one is probably the nicest. So I'm going to stop sharing for a second and bring up Desmos. All right, just give me a minute, guys. All right, so let's put in the one that we just had. So it was -5 minus x divided by x plus 3. And we were looking here for greater than or equal to 0. So you're looking for above the x-axis. And remember, our answer was between -5 and -3. So here's that -5 value. And you can see that going to the right of that, it is above the x-axis. You have that positive idea. Now, remember that x equals -3 was not included. And this is because it actually is a vertical asymptote. So we go all the way until -3, but we don't include -3. And that's because, again, technically you would have a vertical asymptote there that would make the denominator 0. So you can see that you are positive in this region above the axis from -5 all the way till -3. Okay. Now, if you want to look at the original problem, I'll show you what that looks like too. So let's see, it's x plus 1 divided by x plus 3. And then on the right side, you had the value of just 2. So this was graphing the original without bringing everything to one side. I just want to show you how that works. So this was also still greater than or equal to 2. So notice here that above 2, so here's my 2 line just to kind of show you above 2, that starts at -5. So just like the value we had before when we had the 0, you start getting above 2 when you're at -5. So you're actually exactly at 2 at -5. And then going all the way to that y equals -3 is when you will be in that area. So that's just another way to see the answer graphically. They're both really good strategies. Again, I think the 0 one is nice because it's just very consistent. We've been using that a lot. But if you graph the original, you could still see it. So you graph the left and the right side separately. And then remember that in this case, you're looking at greater than or equal to. So you're looking at above that 2 line. So again, both good ways to check visually. And I want to do one more example with you guys. This one is going to be on an application. So there are a lot of applications here, and one of the most popular for quadratics is any sort of thrown object or a falling object or a dropped object. They mirror a quadratic. So if you throw an object upwards, although initially it may look like a straight line, it will kind of reach a peak and then fall back down. So whenever you have a thrown object with an initial velocity, so like an initial speed, or throw or kick, whatever you're doing, it does have that kind of U-shaped pattern to it. So they are always quadratic. So any object that is falling or even vertically projected into the air has a height above the ground of s in feet. And it's given by this formula here. V0 is the initial velocity, and velocity is another word for speed. So it's that starting speed with which you would, let's say, throw the ball. T is time in seconds. And S0 is your original or starting height. Initial just means starting. So a lot of times we use that little sub-zero to mean our initial or starting values. So that would be your starting height. And let's do an example. So let's say a ball is thrown vertically upward from the top of the Leaning Tower of Pisa, which is 190 feet high. It has an initial velocity of 96 feet per second. And we want to know during which time period will the ball's height exceed that of the tower. So meaning be higher than the tower. Now your book does have an image of this. So let me just bring it over real quick. I didn't copy it into the lecture, but you can kind of see it here. So here's someone sitting on top of the Leaning Tower of Pisa. They're going to throw this ball upward. It's going to go up higher than the tower, and then eventually it will fall back down, right? So our question is, when is it higher than the tower? That's really what we're looking at. So let me just kind of draw a quick graph here of that, or I guess not a graph, a picture. There we go. All right, so here's my Leaning Tower. Again, not the best graph picture, but you guys can get it. Okay, so there's my Leaning Tower. And let's say that someone is up here, right? And they're taking that ball and they're throwing that ball. So it's going to go up and it's going to come back down. And this is 190 feet high. So we're looking at this area here. So we're looking at when is the height here above the tower. That's our goal. So what we do is we take our general format. And we're going to plug in what we know. So our initial velocity was 96 feet per second. So this is going to be plus 96t. And our initial height is going to be 190 because we're, right at the top of the tower. And what we want to know is when is this, so S is your overall height, going to stay greater than 190, right? We want to know when is that ball going to be above that 190 mark, right in here. So we can solve this. And it is an inequality. It's a polynomial inequality. And what we can do is subtract that 190 to the other side. So basically whatever height is that you're looking at over here, that's going to be on your right-hand side, whatever height that you want. Now, 190 happens to cancel on both sides, which is fine. So you're looking at negative 16t plus 96t is greater than 0. This one does have a GCF, so I can take out negative 16t. I do like to take out the negative first usually if it's out front. So this leaves me with just t, and then 96 divided by negative 16 is negative 6. So now remember, you're actually solving the equation here to get those boundary points. So I have negative 16t equals to 0 and t minus 6 equals 0. Here you're divided by negative 16 and you get 0. Here you're adding 6 and you get 6. So our boundary points are going to be at 0, 1, 2, 3, 4, 5, and 6. And then you're going to pick test points in between. So here, I can choose, let's see, -1, I can choose +1, and I can choose 7. And I'm going to plug it into this simplified formula right here. So for the first one, -1 squared is just 1. So it's negative 16 minus 96. This is clearly going to be negative. At +1, I have negative 16 times 1 squared plus 96 times 1. So 1 squared is 1. This gives me negative 16 plus 96, which is positive 80. And then for 7, I have negative 16 times 7 squared plus 96 times 7. So negative 16 times 49 plus 96 times 7. And when I do this, I get negative 112. So here we're looking for greater than 0. So we're looking to be above that mark. So we're looking in the positive area, which is from here to here. We're not including the endpoint. I want strictly greater than in this case, right? Because our question was that it exceeds the height, meaning that it's strictly more than. So our answer is between 0 and 6. So the height exceeds the height of the tower, between 0 and 6 seconds. Okay. Now, hopefully this makes sense, right? If you look at this problem here, when we throw the ball, you're at time 0. It's going to go up first and then eventually come down. So once it hits this 190, now you're at time 6. Also, to the left of 0 doesn't even make sense. So I know we plugged in -1, but really in this case, we don't need to because negative time would not make sense here. Even if that was positive, it doesn't matter. So our answer here is between 0 and 6 seconds. Other examples we often do too are different heights. So we may look at different heights of an object. So your right-hand side, maybe it's not 190, maybe it's a height of 50 or something else. And another common one we look at is typically when the object hits the ground. So if the object is here, and just as a note, that's always height 0, unless it's something different where you're underwater or below sea level. In general, again, that's another popular question is, well, how long does it take the object to hit the ground? So something like that would be height 0.